All right, this is the 2014 polar problem. It's question 2, so we're allowed a calculator. We have two polar curves graphed above. One of them is r equals 3. This right here is r equals 3. And the other one is the other shape that we have. It's just this guy right here. That's this one. And it's graphed between 0 and pi. They've told us that we want to find R, the area of the shaded region. All right, so first thing, let's start at theta equals 0. If theta is equal to 0, we're cutting these theta wedges. So we're going to the pink graph, and we're going to keep cutting to the pink graph until this point right here, which is pi halves. So A, 1/2 the integral from 0 to pi halves of the pink curve. Remember, the formula is the area is 1/2 the integral of r squared. After that point, we switch to the other curve. So at pi halves, we start moving to this other curve, the purple curve, all the way until pi. So 1/2 the integral from pi halves to pi of r squared. Now this one right here, I really don't need to use an integral. That is a quarter of a semicircle. The area of a circle is pi r squared, so that would be 9 pi. And then we have only 1/4 of the circle. Of course, you can do the integral. There's just no reason to. And then when we do the entire integral and put it in our calculators, all of this works out to be 9.708. This part of the question was worth 3 points. The first point came from writing the integrand. The second point comes from writing the limits. And the third point is from writing the, getting the answer correctly. Part B. For the curve r is equal to 3 minus 2 sine 2 theta, we want to find dx d theta at theta equals pi over 6. Well, the first thing we need to do is find out what exactly x is. Remember, x is r cosine theta. So then r is 3 minus 2 sine 2 theta, and then multiply it by cosine theta. Now, since this is a calculated problem, I would put that straight in and go ahead and take the derivative dx d theta and evaluate it at pi over 6. And that works out to be negative 2.366. We get 2 points for this equation, for this part, 1 for knowing the equation for x, and 1 for getting the correct answer. They didn't ask us this, but at this moment, which direction is the curve moving? Well, we know the change in x is negative, so that means the curve is moving to the left. If we wanted to see how it's moving up or down, we would find dy d theta. If we wanted to know if it's moving towards or away from the pole, then we'd look at dr d theta. Part C. The distance between two curves changes. Find the rate at which the distance between the two curves changes at pi over 3. Okay, so let's back out of our graph. We're looking right here, and the distance between the curves is changing. The bigger curve is r3, the smaller curve is this. We don't need to use the distance formula because r is the distance between the pole, between the curve and the origin. So all we need to do is subtract those two. So the distance that we're concerned with is 3 minus 2 sine 2 theta. We want to know how the distance is changing at theta equals pi thirds. When you put that in your calculator, you get negative 2. This means the distance between the two curves is decreasing. They didn't ask us to interpret it, but we should understand what it's saying. Part D. So part C is worth 2 points, 1 for the expression for the distance and 1 for the answer. Part D, a particle is moving along this curve so that d theta dt is equal to 3 for all times bigger than 0. Find the value of dr dt. So I want to find dr dt. Looking at r is a function of theta. So all we can find is d theta dt, but by the chain rule, we know that we can do d theta dt. So then we'll multiply by, wait, hold on. I wrote that wrong. Oops. The only derivative we can take currently is dr d theta, and then we're going to multiply by the chain rule d theta dt. And you can see right there they cancel out. We can find dr d theta. We can do that in our calculator. So we can take this and dr d theta at theta equals pi sixth is -2. They told us that d theta dt is 3. So we know dr dt is -6.